Hey Chem classes, today we're going to be talking about limiting reactants. And before we get started, I just want to let you know, you already have all of the skills you need to do these problems. We're just adding a little conceptual twist to them to make them actually limiting reactant problems. So if you recall from my introductory video, we talked about making grilled cheese sandwiches and how you needed 2 slices of bread, plus 3 slices of cheese in order to make one grilled cheese sandwich. And if you can recall, we did an example problem where I said I had 10 slices of bread and 21 slices of cheese, and I asked you how many sandwiches we can make. And from this we could tell that the bread would allow us to make 5 sandwiches, while the cheese would allow us to make 7 sandwiches. And that means that we could only actually make 5 sandwiches because the bread limits the reactant. Right? So it's a limiting reactant. It limits the amount of product that we can form. That would make cheese our excess reactant in this particular problem. We just want to apply the same idea to more chemical related problems. So let's take a look at an example. How many grams of barium sulfate will be produced when 400 milliliters of 1.8 molar barium nitrate solution reacts with 300 milliliters of a 1.2 molar potassium sulfate solution? How much of the excess reactant will be left over? So right now what you need to do is write the balanced chemical equation. And this is what you should have gotten. So we have aqueous solutions of barium nitrate and potassium sulfate, and they form a solid barium sulfate precipitate plus a potassium nitrate aqueous solution. So again, looking into this problem, what I'm asked for is to determine the grams of barium sulfate that's going to be formed. And the things that I am given, what my knowns are, is that I have 400 milliliters of 1.8 molar barium nitrate. And let's take a second again to remember, 1.8 molar, that big M next to the 1.8, is a unit that means molarity. And molarity is a conversion factor. 1.8 molar means 1.8 moles over 1 liter. We also have 300 milliliters of 1.2 molar K2SO4, potassium sulfate. So once again, we can use this as a conversion factor. 1.2 molar potassium sulfate means I have 1.2 moles of potassium sulfate for every 1 liter of potassium sulfate. Okay, so now let's take a look at how the problem is going to be set up. So tell me what your starting values are going to be. We're going to be doing 2 calculations here. So what are the 2 starting values going to be? Well, you should have told me that you're going to start with the 400 milliliters of barium nitrate and the 300 milliliters of potassium sulfate. Those are our given values, our known values in our problem. Now, we're starting this with milliliters, and we know that our conversion using molarity is in liters. So the first step I'm going to do is convert this into liters. You can do this in your head. You don't have to show me this step if you don't want to. You can just move the decimal point 3 places and start with liters. That's up to you. Here we can see the milliliters cancel out, and I'm now left with liters of barium nitrate. Now I can use that molarity. So I think to myself, what unit do I have? What conversion factor do I have that will let me turn liters into something else? And hopefully that something else is getting me closer to moles, right? Because again, that's where I want to be. And I do. I have molarity. Molarity includes both liters of a solution and moles of a solution. So I use it as the next conversion factor. 1.8 moles of barium nitrate for every 1 liter of barium nitrate, and now I've canceled out my liters. Okay, here I am. Now I am in moles of barium nitrate, so it's time for my magic moment, right? It's time to go to my mole ratio. The mole ratio converts from moles of one substance to moles of another substance. So it actually changes the substance I am talking about in the problem. So I'm going from barium nitrate to barium sulfate, which is my desired product. Now that I am in moles of barium sulfate, I just need to unconvert it, right, in order to get the unit that the problem is asking me for, which in this case is grams. So I know that molar mass is going to convert moles into grams for me, and cross out the moles there. And then lastly, I just do the math, and I'm going to end up with 168.04 grams of barium sulfate. Okay, a few too many sig figs there, but that's okay. Let's do the same thing for the potassium sulfate. So we start with 300 milliliters of potassium sulfate. My first step, again, is going to be to convert that into liters. And once I'm in liters, I can use the molarity of the potassium sulfate in order to tell me how many moles of potassium sulfate I have. Okay, and now that I'm in moles, I am ready for my magic step, right? I'm ready to use my mole ratio in order to convert from the potassium sulfate into the barium sulfate. So I have made my magic move here into barium sulfate. Now the problem is exactly like it is on top. I need to multiply by the molar mass of barium sulfate, and I get a final answer here of 84.02 grams. So which is the limiting reactant? How much barium sulfate can I make in this reaction? If you said 84.02, you'd be correct, right? Because what's going to happen after I have used up all of my potassium sulfate, I've made 84.02 grams of barium sulfate. I'm all out of potassium sulfate now. I don't have enough left to make up to 168.4 grams, which is what the barium nitrate would have let me make. So whichever one makes the least indicates which is the limiting reactant. So the potassium sulfate is the limiting reactant in this problem, making the barium nitrate the excess reactant in this problem. And now I can see that I'm going to be able to form 84.02 grams of barium sulfate, after which the potassium sulfate will run out and the reaction will stop. Okay, so now I need to know how much of my excess reactant, how much of my barium nitrate is going to be left over after the reaction stops. So I'm going to go back to my I'm going to go back to my 300 milliliters of K2SO4, but this time I'm going to determine how much barium nitrate would be used up by using the 300 milliliters of potassium sulfate. So first off, again, I'm going to convert this to liters because I know my molarity is in liters. And then again, molarity will allow me to convert the liters into moles. Once I have moles of K2SO4, I get my magic step now, right? I get to transform moles of K2SO4 into moles of barium nitrate. Now it's simply a matter of converting it to the volume that I need, right? Because I know I have a volume of barium nitrate. So I want to end with a volume of barium nitrate in this question. Right now I have moles of barium nitrate, so I'm going to use my molar quantity, my molar concentration, but I'm going to flip the conversion factor, right? Because now I want liters and I want to cancel moles. So 1.2 moles goes on the bottom and 1 liter goes on the top. Right now I'm in liters of barium nitrate, and I want to go back to milliliters because that is what the problem gave me, right? Gave me a value in milliliters. So I'm going to go back to milliliters, do this math, and I'm going to end up with 200 milliliters of barium nitrate. So if we go back to the original problem, we'll see that we were given 400 milliliters of barium nitrate. So how much barium nitrate is going to be left over? Simple subtraction, 400 milliliters to start, 200 milliliters used up in the reaction. That leaves 200 milliliters of barium nitrate left over. Okay, so let's take a look at the problem as a whole. This is back to the original problem. How many grams of barium sulfate will be produced? Well, we figured that out, right? Barium sulfate is what we determined in the first steps. We also determined that the potassium sulfate is the limiting reactant and the barium nitrate is the excess reactant. We were able to determine that 84.02 grams of barium sulfate would be produced and that 200 milliliters of barium nitrate would be left over. So this is a full limiting reactant problem. You need to find what the limiting reactant is, and that will help you to determine how much of your product will form. And then often you will be asked how much of the excess reactant is left over. And in that case, you do one more final calculation in order to determine how much of the excess reactant is used up. Okay? So again, all of this involves conversions that you already know how to do. So it's just adding the concept of the limiting reactant on top of the conversions that you already know how to do.